Hey guys, good evening. Good evening. Welcome to the live lecture session for week 5, CS 75 reinforcement learning. So apparently I had taken the class from 7 to 8 p.m., but I had forgotten to switch on the uh, Google Meet recording. So I don't have the uh, recorded meet in which the students had joined. That's why I'm re-recording it again so that I can put it on YouTube. So sorry about that. I'll just quickly redo the entire live session, what I had done uh, today evening. So we start with the week 5 lecture part. So my name is Manav. I am one of the TA for this course. And so what I have planned today is I am going to do a quick roundabout of what has been covered in week 5 till now. I'll take around 20-25 minutes in that. And then in the remaining time, I'll be solving one of the MDP word problem. And then we'll look at some coding related issues because it's necessary for you guys to have some hands-on experience to in this course. Okay. So today I'll uh, be dealing more on the practical aspect of reinforcement learning. Okay. So if you remember last week, I had given this question to you. So there was this word problem on MDP wherein you had to design the MDP, write down all the possible states, actions, rewards, the transition probabilities, and then draw the MDP. And based on that, you had to perform value iteration, policy iteration, as well as discuss the similarities or difference that you obtained here. Okay, so you guys had to do this. If you have done it on your own, good. If not, I'll be solving this today in class. But before that, I should quickly just uh, finish all that has been covered in the lecture in week 5 lecture series so far. So I'll quickly come back to that. So week 5 lecture mainly contained 4 topics. It uh, included value iteration, policy iteration, some introduction to dynamic programming, and Monte Carlo methods. Okay, so we start with value iteration. So the value iteration algorithm looks like this. This was what professor had noted in his class. So I have just noted it down. So the algorithm looks like this. So you initially select some v functions. You initially select some a value function with v naught, which belongs to the space of v. You pick an epsilon which is greater than 0, and you set n equal to 0. Okay. And then now for each state in the state space, you compute vn plus 1 by using the Bellman equation. Okay, so this is the Bellman equation which is mentioned over here. This is the Bellman equation, right? So based on that, you compute your v n plus 1 s, right? And after that, you check if the updated vn and the previous vn, how close they are to each other. If the updated vn and the previous vn are bounded between this quantity, then you go to step 4, increment n by 1. Otherwise, you continue with step 2. Okay. So this is apparently some magical number that appears on the right hand side of this inequality. So you get this. This is sort of back engineered, reverse engineered, so that in the end, when you prove the theorem, you get v pi minus v star to be less than epsilon. Okay. So this is some backhanded trick to arrive at this number. And then after you have done that, then you once you have met condition 3, that means you have obtained the optimal value function. Now once you have obtained the optimal value function, all you need to do is to obtain the optimal policy, and to do that you just need to roll out the value function along the policy. That means you basically do a pointwise argmax over each state in the policy, right? So you do this step, which is for each state S, you find the optimal policy, the pointwise optimal policy, and after that, what you end up would be pi star. Okay, so this is the value iteration algorithm. Okay, so you should note here that uh, the value iteration algorithm converges to the optimal value function, but it converges to the near optimal policy. Okay, so this is an important difference. So this was another theorem which was proved in class by professor. So So this theorem is that given an initial state v0, and let's say we have the Cauchy sequence vn, which is derived from the Bellman equation. So then we have these four proofs. Okay, so the four proofs look as follows. So v of n converges in norm to v star. Okay, then there exists a finite n at which condition 3 is met for all n greater than n. Okay, and the third and fourth condition is that the pi defined by mm, step 4 is near optimal, and that vn plus 1 minus v star is bounded by epsilon by 2. Okay, when 3 holds. So this is the these are the four conditions that this theorem proves. You can refer back to the proof that sir had given in class. I just wanted to uh, quickly round about what has been covered in week 5 lecture, right? And next up, we have the policy iteration. So instead of getting the value function to converge to the optimal value function to v star, instead we start with the policy and directly deal with it. Okay. So policy iteration typically consists of two parts. First is the policy evaluation, and second is the policy improvement. So note here that first you do policy evaluation, then you do policy improvement, and this happens simultaneously, this happens sequentially rather than simultaneously. Okay, and the way policy iteration works is as follows. So you select arbitrary pi 0 in the beginning and set n equal to 0. Then first you perform your policy evaluation. So the policy evaluation so your policy evaluation is in the policy evaluation, first you initialize your pi 0, and based on that pi 0, you compute the v pi of n, the value function for the policy that you have. Okay, you basically evaluate your policy, and you compute your respective v pi n, and after that you try to improve your policy. So next you choose your pi n plus 1 such that it maximizes the Bellman equation, but instead of v star here, you have your v pi of n. So this is not v star that you're maximizing over, but rather the v pi of n. So you're improving on the policy. And then the stopping criteria is that once you have your pi n plus 1 to be equal to your pi of n, then you declare that whatever you have is your optimal policy. Okay, but you have a stopping condition that pi of n plus 1 is equal to pi of n. So for this stopping condition to be true, we should typically show that my pi of n plus 1 should always be greater than or equal to pi of n, correct? So in order to show that, you have to prove this quantity here. So in order to show that, you have to prove that sorry, you have to so in order to show that, you have to prove that the respective value function. Okay, so my value function v pi of n plus 1 is greater than equal to v pi of n. Okay, and this was what professor did in the lecture series. You should go back and look. So this basically essentially ensures that my condition 4 is met, and that is my stopping criterion. Okay, so this is policy iteration. So policy iteration is, like I said, it's basically a sequence of policy evaluation and policy improvement. So if I were to represent it, I would write it like this. So I have my pi 0 initially. I do my policy evaluation. Okay, and when I do policy evaluation, I typically get my v pi of 0. Okay, and after I get v pi of 0, I do my policy improvement, wherein I get my pi of 1, and accordingly I do evaluation. I get v pi of 1, improvement, I get pi of 2, and so on. Okay, till till I end up with my sorry, till I end up with till I end up with v star, and on improving I get my pi star. Okay, so this is what my policy iteration algorithm looks like. Okay, right, and yeah, so this was policy iteration. So we have value iteration, we have policy iteration. both typically do the same thing. They both give me the optimal value function and the optimal policy. But the difference here is basically the rate of convergence, which the number of iterations or the number of the number of iterations I need to follow in order to converge to the optimal value. So typically, it has been seen that policy iteration has a faster rate of convergence. It converges faster to the optimal policy as compared to the value iteration method. Okay, so we'll see that in the example that I have given. So we'll solve that question in class and show that this actually is true. Okay, so I have some codes ready. I'll show it to you once I finish this roundabout. Okay, yeah, sorry. So next up, we'll look at something known as a dynamic programming. Okay, so in dynamic programming, what happens is you typically use the knowledge of whatever you have till state s of n, and then in order to improve on state s of n, no, in order to compute the value of state s of n plus 1, you use the previous knowledge of state s of n. This is typical dynamic programming. So to visualize this, you look at it like this. So let's say you have an MDP wherein you have two states. You have the initial state, and the first action that you take leads you to the terminal state. Okay. So once you have that, all you need to do is you need to compute the value function once, and you converge to the optimal value function, right? So this v of s of vs plus v of s1, whatever I've computed, is the optimal value function. So now next, if I add up some previous states to it, so let's say I have some state s2 and I need to compute the value function for that. I only need to know the associated value function with state s of 1, state s1, and then I can continue doing that. Okay, so this is my dynamic programming approach. But there are certain drawbacks to this approach. The first one being that it requires a sweep over the entire state space. So whenever you do the value function backup or the value function update, you need to do the backup over the entire state space that you have. Okay, so major drawback for the dynamic programming approach. And second is that this can be computationally expensive. So let's say you have an MDP with millions and crores of states. So doing this sweep over the entire space multiple number of times when you're doing your value iteration or your policy iteration would be problematic. Okay, this is computationally expensive. So so dynamic programming basically approximates the return that you have, something like this. So let's say my total return looks like this. Okay, so this is my total return. So this is the total complete return that I have. So my dynamic programming approach, my DP approach, approximates it as follows. Okay, so this is the total return, and this is written as V of ST plus 2. Okay, so what has happened here is that the entire term after gamma has been truncated or has been approximated by this value function of, has been approximated by the value function of VST plus 2. So this is the approximation that dynamic programming typically deals with. So computing the complete return is computationally expensive, right? Because I don't have like the access or the means to keep looking back and to keep looking into the future and do the update behind, right? So this is the dynamic programming approach in such cases. So you typically don't have access to the complete return, but rather some approximation, the first order approximation of the reward function that you have, right? And since we know that the dynamic programming has several drawbacks, so there is another method known as asynchronous DP. So asynchronous DP is typically an in-place iterative DP algorithm. So what it does is, so these algorithms, they back up the values of states in any order. So you do not, for any update of the value function, you do not need to do a complete sweep of the entire state space, but rather it provides some sort of a flexibility, right, in terms of backing up the values of states in any order. So this thing is not organized in terms of the systematic sweeps. But however, for convergence, the algorithms must continue to back up values for all states. So if you want to do convergence, the algorithm eventually should back up all states, But at each step, it should not back up all the states, but it provides some kind of flexibility. Hence the name asynchronous dynamic programming. Okay. Next up, we have something known as a generalized policy iteration. Okay. So the generalized policy iteration is different from a policy iteration in the following way. Okay. So my policy iteration typically looks like this. So I have my policy evaluation. I have my policy improvement, and I keep doing it repetitively, right? So the difference here is that in policy iteration, I do my PE and PI, sequentially, right? So once I have done the complete policy evaluation, only then I go for policy iteration and so on. Policy, the generalized policy iteration or GPI is different in the following factor. So in the following way, I need not do a complete sweep over the entire space whenever I'm doing the update. So I typically only, I can, I also need not do the complete policy evaluation before doing the policy improvement. I can basically play around or do partial policy evaluation and partial policy update for different states and not the entire state space. Okay, so this allows this flexibility, and asynchronous DP also provides this finer, fine tuning between different aspects of policy iteration, right? So what happens is in policy, in the normal policy iteration, you have the evaluation and iteration, which is happening in a circular fashion sequentially. But in generalized policy iteration, it so happens that they sort of compete as well as conflict with, as well as cooperate with each other. So I have basically two optimization algorithm. I have my value. I'm evaluating the value function in the. I'm evaluating the policy wherein I'm basically optimizing my value function, and in policy improvement, I'm optimizing my policy, right? So what happens in that case is I'm trying to obtain the optimal policy and the optimal value function. In that case, I'm trying to converge to this point over here. So here you see the value function, my V star affects my pi star, and similarly my pi star affects my V star, right? So, yeah. So this is my GPI, and if I were to represent it diagrammatically, it should look something like this. So I have, this is, let's say, my V, which is equivalent to my V pi, and this is pi, which is greedy with respect to my value function, right? So initially, I start with some estimate of my value function, which is, sorry, which is V0 and pi 0. I start with this estimate, then I do policy evaluation. Okay, I end up with some value function, and then based on that, I do a policy improvement. So I move closer towards the optimal value function. Then there's a policy evaluation improvement, and so on. So you typically do it few number of times until you eventually end up with the V star and pi star. Okay, so this is my uh, typical generalized policy iteration, right? Next up, we have something known as a Monte Carlo, the Monte Carlo method. So in Monte Carlo method, the important assumption that you have is that we don't assume complete information of the environment. Okay, that means I do not assume knowledge of the policy pi or the state transition probabilities or any other factors in the environment, but rather if I want to do my update, so I do that by sampling experiences from repeated interactions with the environment. Okay, so Monte Carlo approach requires samples from simulated interactions with the environment. So based on the sample that I have, I typically try to reach the terminal state and evaluate and obtain my trajectory or the policy. So let's say I have my state S, and this is my goal state T. So if I want to reach there, I repeatedly draw thousands and thousands of random samples until I eventually reach state T with my policy. And then whatever states that I have, in between, they form a part of my policy pie, right? And I get there by doing some backup summation, right? So this is like summation over the rewards or the returns that I have. Okay, so this is how I get here. So these require only experience samples from simulated interactions with the environment. The model needs only the generated sample transitions, and they don't require the complete probability distributions of all samples, right? And then MC methods, they sample an average returns for each state action pair that you have. So this is very much similar to the bandit problem. In the bandit problem, what you're doing is you're pulling an arm, right? So here you're taking an action, or rather uh, computing the reward for a given state action pair. You do it multiple times. You compute the return, compute the average return for each state action pair. So this is similar in that way to the bandit problem, right? So this is the Monte Carlo approach. And yeah, so this is how it looks like. So like I mentioned, this I start with some state S, and my goal is to reach the terminal state. So whatever state I obtain in intermediate form a part of my policy pi, right? And yeah, so, so this is the sum over all the returns that I have obtained so far. So so in typical Monte Carlo, if I were to represent it by means of state uh, update or state action pair. So let's say this is my state S1. I start here, and in that I take action A1. I reach state S2, reach here, and so on till I reach some final terminal state S of n, right? So let's say this is my terminal state. And then, so in order to update the value function here, or I need to basically do a backward update of all the states that are present in the chain over here. So I need to basically, in order to update this state, I need to go back in chain. I need to update this state, this state, this state, and so on. Okay. So this is what typically happens in Monte Carlo. So I should have access to the entire uh, I should have access to the entire horizon or the entire trajectory, and then any update that I make in that horizon should typically move back in chain. I update all the states accordingly. Okay, so this is how my Monte Carlo looks like. And compare this to your TD approach. So your TD approach, typically what it does is you have the state S1 and then A1, and then you have some estimate of the next state that you have, and so on until, and you do that until you reach your final state S of n, right? So typically, if I were to uh, update, let's say state S2, so I only need to look one step behind. Okay, because this is what my TD approach tells me. All I need to do is take a look back at one step behind in order to do the backup here. So in Monte Carlo case, I need to do an n step backup, whereas in the TD approach, I am required to do only a one step backup. This happens because of the return that is accessible, right? So in Monte Carlo, you have the complete return. Okay, so this is what you have access to in the Monte Carlo approach, and in the TD approach, you only have the truncated value function, which approximates the further future rewards. Okay, so this is an approximation of the rewards. Okay, so this is a first order approximation that you're making in TD approach. Okay, yeah, I think I think that was all for Monte Carlo, which was covered. We'll be looking in detail policy Monte Carlo and other stuff, T0 approaches in more detail in week 6. So before moving to the questions, I will quickly discuss the solutions of the week 5 assignment, and after that, we'll look at the codes. Okay. So let policy and value functions iteration on a finite MDP be of n and v pi of n after the stopping criterion is met. Okay, so this is for policy iteration. Then I know that eventually I'll end up with v star and pi star. So pi n will be the optimal policy and v pi of n will be the optimal value function, right? So this is the correct option. Then I have an assertion reasoning question. So Monte Carlo policy evaluation must use exploring starts in the case of non-deterministic policies. The reason is they have to rely upon exploring starts in the case of non-deterministic policies to ensure adequate sampling of all states. So here the issue is that Monte Carlo policy evaluation uses exploring starts in the case of deterministic policies. But here in both the assertion and reasoning, they have mentioned about non-deterministic policies. So both of them are incorrect. That's why this option is true. Then you have which of the following is/are are guaranteed to be true at the stopping criterion. Okay, so I just need to look at the stopping criterion. If I know this thing, what all would be true? This is true. This is true. This is true, and this is true, right? Yeah, I think this all is true in this question. Yeah. Okay. Next up, we have like consider an MDP where there are n actions, each of which is applicable in state S. So if pi is an epsilon soft policy and q pi be the action value for policy pi, then consider the following statements and choose the appropriate option. Okay. So the assertion is any epsilon greedy policy with respect to q pi is strictly better than pi. And the reasoning is that in an epsilon greedy policy, the action with maximum estimated value is chosen with probability 1 minus epsilon plus epsilon by L, and other actions are chosen with a random probability of pi by n. Okay. So both are correct, but the reasoning is doesn't really answer the assertion that you have made over here. So that's why this is the correct answer. Last question is if V satisfies the Bellman equation, then if the Bellman equation is satisfied, that means my pi is an optimal policy and V is the fixed point of pi. So this is the correct answer. Okay. Yeah, I think we have covered all the was taken in class. Now we'll quickly look at the word question that I had given last week, and then we'll look at the coding part. Okay. So this is the word problem here. I'll read the problem and then we'll solve this. Like first we'll draw the MDP and then we'll look at the solution. Okay. So I read from here. I've written down all the states and actions. So my states are hostel, acad, building, and canteen. And my actions are either attend or eat. Okay. So I'll just read through it. When the hostel is at student, he or she attends classes by going to the academic building with 50% probability or staying in the hostel with 50% probability. So attending has a 50% probability of leading me to the same state, or I attend with 50% probability at the academic building. When hungry, he or she goes to the canteen with 100% probability. So if I'm hungry, I take action eat with probability 1. From the academic building, student attends classes where he stays in the academic building with 70% probability and goes to the canteen with 30%. So this is attend 70%, and attend from canteen is 30%. When hungry at the academic building, he or she goes to the canteen with 80% probability and stays at the same place with 20% probability. When hungry, he or she goes to the canteen with 80% probability or stays at the same place with 20% probability. At canteen, the student has 60% chance of attending classes by going to the academic building. So from here, I have a 60% chance, 30% of chance by going to the hostel. So I attend with 30% probability and attend here with 10% probability. If hungry student stays at the canteen with 100% probability. So if the student is hungry, stays at the canteen with 100% probability. Okay. So this is the entire MDP that we have. So I'll just quickly show how we can perform your policy iteration and value iteration in this case. Okay, so I hope my screen is visible. So I'll quickly look at the problem that we have. So this is the campus problem. I have written down the given states, actions, and rewards. So my states are hostel, canteen, and academic building. I have labeled it as 0, 1, 2 respectively. My actions are either to attend or eat, which has the label 0 and 1. These are the respective rewards for being in the respective states. The gamma I have taken to be 0.9. And the data here, this is the data that I have written over here. Okay. So I'll just quickly copy paste this in the chat window if you this one. So this is the first problem. So this is the data for the hostel when I'm at the hostel. So this is the for each action, I have the probability, next state, and the reward associated with each action for each state, right? So for each, so I have the data for each state action pair. So this is for the hostel, this is for the canteen, and this is for the academic building. And the value iteration looks like this. So this function basically gets me the maximum value function or the value function update. So this is the def max function, and this is my value iteration step. So I initialize my value function to be 0. My threshold here is 0.001. The threshold is the epsilon value that you saw in the in the value iteration algorithm. My delta is 1. We'll see what delta is. And my policy is initialized to be 111. So my policy initially is some random action that we have. I've taken iteration to be 0. And here I show while delta is greater than threshold, I perform the value iteration, check the delta, see if delta is less than epsilon, which is my stopping criterion, and then increase the iterations and so on. And once I perform this, I'll quickly run this. Once I perform this, you see the policy that I end up with is this. So the optimal policy here says that from all states, the agent should choose the action to attend the class. And the value function is that the above cell shows that the optimal value function for hostel, canteen, and academic building respectively. So this is the respective value functions, right? And then I just print the number of iterations it took to reach there, and it took 74 iterations. Okay, so this was the value iteration method. Then we take a look at policy iteration. So I have my value function v, which is 0, 0, 0. I have my policy, which is initialized to some random policy. Iteration is 0. Here, I typically do two things. So one is policy evaluation and one is policy improvement. Okay. So in policy evaluation, I do the entire thing that happens in policy evaluation, wherein I compute the value function, and then policy improvement, I take that value function and choose my pi of n+1, right? So when I'm calling policy evaluation, my policy improvement gets called inside this loop itself. So I just need to run this code. So I have this to be my optimal value function. You can see that this is very similar to what we had obtained in the value iteration. And the policy also is the same. The optimal policy says that from all states, the agent should choose the action to attend the class, right? But interestingly, the number of iterations it took here was only 3. So it shows that my policy iteration has much faster convergence as compared to my value iteration, right? So this is the discussion. As we saw, the optimal value converges to almost the same values for both value iteration and policy iteration with the respective value functions for each state. Also, both the algorithms predict the same optimal policy to attend from each state, be it a hostel, canteen, and academic building. Yeah, and the difference here is in the speed of convergence. Okay, so my policy iteration gave faster convergence and as compared to my value iteration, but both of them converge to the same values, the same value function and the same policy. So this is important. So we showed this through this example. Okay, so this was the take home problem that I had given last week. Okay, so after that, we should take a look at another implementation of the Q-star algorithm, something known as the frozen lake environment. Sorry. So this is basically a grid world problem. So this is a 4x4 grid wherein there is an agent at the top left corner and it has to reach the bottom right corner. So the surface it has is a slippery surface. It has ice on it. The agent should walk on the icy path, but not fall inside the hole here. Okay. So if the agent falls into the hole, then the episode is over. It again starts from here until it reaches the goal position. So the agent gets a reward if it doesn't reach the goal or it falls into a hole. And in the end, when it reaches the goal, it gets a reward of 1. So this is how the environment is defined. So the typical state space here looks like this. So each row and column, the row and column at which the agent is at defines the state for that. And in addition, what I have done is I have added an additional information, which is the direction to the goal. So if the agent is over here, the goal is in the direction of southeast. So agent should move in the southeast direction. So this is an additional state information that I have added in the custom added in the original frozen lake environment. This is a gym environment. You should take a look at this. So this is a slightly modified problem in that sense. And the action here is to either take up, down, left, or right. So here the action is probabilistic rather than deterministic. It means that if I take an action to go to the left side, so there is with certain probability, because the ice is slippery, I can either move to the take the up action or the down action, because so I can take perpendicular actions if because of the slipperiness, right? So let's say if I'm here and I want to move to this side, so there is with some probability I can go in this direction or in this direction. Okay, so let's say so the probability here is 1/3, 1/3, 1/3. So if I'm here and I want to move this side, so I go in this direction with a probability of 1/3, and I go here with probability 1/3, and here with probability 1/3. So there is this uncertainty in the environment because of the slipperiness. Okay, so I do not always take the action that I desire to take. So this is how the environment looks like. So this is the initialization with all the imports that you have. And this is how the frozen lake class looks like. Should share this also. Okay. Uh, so this is how the frozen lake class looks like. So this is the initialization where all the initialization for the rows, columns, the goal position, and everything is done. Should take a look here. This is the entire initialization of the environment. And then there is a step function. So the step function basically takes the input action that you have selected, and based on the action that you have selected, what it returns me is the next state, the reward. D is the done condition. So it's basically the stopping condition. It says whether the goal has been reached or not. And this is some additional information, or this is the probability with which I'm taking the action that I'm supposed to take, or what action that I ended up taking. Right. No, okay. It tells me the probability with which I have taken that particular action. Okay. So this is what the step function contains. It contains the information about the it basically if you after you take the step, it updates the environment accordingly, right? And gives you the reward for it. Okay, so these are some additional functions. Then there is this reset. So once you call reset, it basically uh, initializes your environment to it takes your environment to the initial condition. Okay, so this is the reset. So you typically do in this reset the environment after the episode has ended, or you have fall into a hole or something like that. So this is the reset function. Then this is the bearing function. So bearing basically gives me the direction to the goal. So I know which direction my goal is at. I use this bearing to move to the goal direction. So these are two functions to compute the bearing. And there are other functions. So there is this render function, which gives me this nice plots to look at. Uh, so this is the entire frozen lake environment, right? So this was initialized here. Next, I take a look at the frozen lake problem. I import all the necessary stuff. And this is the environment that I have created. So this F represents the frozen surface. H represents the hole. So here you notice I haven't given a start and goal location. So this is something that I'm doing randomly here. So I select any of this F over here and flip it into an S, which is my start position. And similarly, I randomly select any of the F that I have and convert it into my goal position. Okay. So if I look here, my action size is 4 because I have 4 possible actions, which is up, down, left, right. And my state size is 144. So 144 because for each row and column, I have 9 possible directions to go to. Okay, so these are the 9 possible directions. Here means that I have reached the goal, and there are the 8 possible directions, which is east, northeast, north, northwest, west, southwest, south, and southeast. So these are the 4 possible directions. Uh, so my total state space is basically 4 into 4 into 9. So 4 is 16, 16 9 is 144. So I have total 144 states. Okay. So my Q table, if I take a look at my Q table, so I initialize it to be the size of my state cross action space. Okay. So these are the hyperparameters that I have defined. So the total number of episodes is 15,000 that I'm training it for. You can train it for more number of episodes. My learning rate here is 0.7. So my learning rate here is the step size parameter, the alpha that you use in the Bellman. No, not when you are doing the Q update, right? So max steps here is 99. So it means that after 99 steps, if I haven't reached the goal, then I stop the episode. I reset it again. My gamma here is 0.95. My epsilon here is 1.0. Max epsilon is 1 and min epsilon is 0.01. This is for my epsilon greedy. And this is the decay rate for my epsilon. I start with epsilon 1 and then I slowly decay till I reach 0.01. This is the list of all my train rewards and the list of the epsilons. So I start here. I for each episode in the total number of episodes, I perform the Q learning. So this is the Q table update that I'm doing here. And once I've done that, this is for 15,000 episodes. Once I've completed it, I get the Q star action for each possible state. So for each possible state, I have the action that I need to take, whether I need to go left, right, or in some other direction, right? So yeah, so this is what my Q learning looks like. So once I've trained this Q table, all I need to do is I need to test it out on different possibilities and see if it is actually working or not. So I run it for, let's say, five different times. So what we see here is that I had initialized my start and the goal position to be here and here, and we reached our goal in 7 steps. So if it was the ideal condition, I should have reached in 2 steps. I should have taken the down action and the left action. But since there is slipperiness, it might have happened that I wanted to go down, but I ended up going up, okay, or some other direction or some other place. So due to this, the number of steps will vary at different time steps. Okay. So this is the beauty of this problem. So Otherwise, you would have gotten the number of steps to be 2 in all the cases, in the optimal Q values, right? So see here again, I'm reaching goal in 5 steps. Here I reach it in 2 steps, which is the minimum number of steps. Then there is 5 steps. Okay. Yeah. So you can have a look at it. So in this part, what I've done is I had initialized the start and goal position in the beginning itself, and I did the training with a fixed start and goal position. So what you can do is you can also try this frozen lake with random start and goal position. So here you can define a bigger size of the environment. Uh, and here what you can do is you can set your start and the goal position inside the for loop in itself. Okay. So for each episode, I'm changing the start and the goal position. So this is more generalized type of learning. So you can try around with that and see how the results come up. So yeah, you should take a look at this, right? So this is the frozen lake environment. I hope this was clear. I have shared the codes with you. You can modify it and play around with it. Okay, so this is the frozen lake problem. And lastly, we come to this part. Sorry. So this is the warehouse problem. This is a problem that I had given in the last lecture. So this is supposed to be a long question that I expect you guys to code it and solve and solve and figure it out. So the environment works in the following way. So I have this agent. The agent needs to push this box to this location. So the agent cannot grab and pull it. It can only push it from behind. So in order to reach here, the agent should come here, go here, this way, push the box here to this wall, then move here, and then push to this position. So I think this is the shortest possible path for the box to reach the goal. Of course, there are other possibilities. The agent comes here, pushes the box, then moves here, pushes here, and then goes here. So this is a longer route, but the easiest path is go here and then push from here. Okay, so this is the environment that you have. So I have defined the environment for you guys. So you have the the entire environment is encoded here. So I'll quickly discuss. So this is the warehouse environment. So this is the initialization for the environment. So this defines the grid dimension, which is 6 cross 7. The agent position, you can fix it to be 1 cross 2 at 1 comma 2 for every episode. The box location and goal location can also be fixed. And then there are certain actions, the position of the wall, and the stuck location. So the stuck location is that you should ensure that the box doesn't reach to a corner of the wall where it cannot be pushed further. So if it reaches certain states, let's say here, 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 the episode ends because there's nothing to be done. You can't push it further, right? So these are the stuck locations. And then this is the reset function. What to do in the reset function is once you call that, the environment is reset to its initial state configuration. Okay, so when you call the reset function, the agent goes back to 1 comma 2, box goes to 4 comma 3, and goal goes to 3 comma 1. Okay, and this is a step function. Step function basically takes in action as the argument, and it returns new state, which is what you get after taking action A from your previous state, the reward for taking that action, and done is the stopping condition. It's a Boolean value to determine if the episode terminating condition is reached. Okay, so this is the entire uh, function for the step function. Then this is the render. So this basically uh, gives me the visualization of what is happening in the environment. Okay, so this I have done using matplotlib. With time, I'll also improve the code. I'll also make it better so that it looks better. But I expect you to do most of the stuff here because this is supposed to be a long sort of an assignment. I don't expect you to solve it in the next 2 weeks, but take your time. You should get familiar with the working of this environment so that you can test different algorithms and see what you want to achieve. Okay, so this is given to you uh, with the thinking that since you have been reading a lot of theory about reinforcement learning, I think it's necessary that you guys have some practical implementation of the stuff that you're doing, or you need to code some stuff. So I expect that you use this to code different. You use this environment to code different or to implement use this environment and implement different reinforcement learning algorithms as you learn in this course. Okay, so here in the step function, the action that you have, this action is given by your RL, uh, whatever RL algorithm that you're implementing, right? So here I call the warehouse agent. So I'll just quickly run this. So this is the environment class. You call this environment here. So I'll just show how it works. Okay, so when I do this, when I do agent.reset, this resets the environment to its initial position. Okay, and when I do agent.step, right? So if I take a random step, let's say I take action 0, so I uh, go to some next state, I get some reward, and then I get a like Boolean condition if it's true, false, or something like that. Okay, this I'm just taking random action. This is how it looks like. And if I do agent.render, so it shows me the position of where the agent is after doing whatever I want to do. Okay, so this is how the class works. So here what I'm doing is I'm just showing this thing. So I did my start and I've defined my start and done here. I did agent.reset, and then for a for loop, I am running a for loop for 10 steps. Here I'm taking some random actions and showing how the agent behaves. Okay, so for uh, for a for loop with 10 time steps, I am taking random dot sample of the actions. Then based on that, I am getting the agent location, which is the next state, the corresponding reward, and then done when I take action, which is given here. So here, instead of random dot sample, you should use the actions that you have, which you obtain from the optimal policy that you get from your RL algorithm. So one exercise for you would be to try out your value iteration, your policy iteration that I've shown here. You should try this out in this environment. So you can play around with this environment so that you get familiar with uh, the coding aspect of RL, right? Okay, so this rendering I have done using matplotlib for now. You can obviously improve on it and uh, do it in a better way. So this is just a crude representation, right? So here I've taken random actions and see where the agent goes at. So initially it's here, it moves here, in the next step, it comes here, goes here, stays there, moves up. It's taking some random action. It's pointless right now, but you need to make it behave in such a way that you know it pushes the box to the end position. The episode ends only when it pushes the box to the end position, right? So yeah, so I have done the part for you. I have defined the warehouse environment. You have all the information. You have the rewards defined. You have the states space. You have the action space. You have the stuck conditions. Everything is defined in this environment. All you need to do right now is uh, take this class, play around with it, come up with your codes for the other algorithms that has been discussed or will be discussed later on, and implement on this. Okay, so we can discuss this in more detail in the coming weeks, right? So I think that's all I had for today's class. If you have any questions, do hit me up. Otherwise, I am done with whatever I had to present today. Okay, I think this is a good time to stop. Thank you for attending and uh, have a nice weekend. I'll see you in the next class. We meet again next Friday at 7 p.m. Okay, thank you. Bye. Good night.